So let's go right into the processes that are of interest for near equatorial precipitation distribution. We'll start by recapping the basics we saw before. So here it is in colors, temperatures for June, July, August, and December, January, February. And as you can imagine, as the ITCZ moves north, both the maximum humidity and warmest temperatures move north. Temperatures drop off with altitude because of deep convection, and coldest temperatures in fact occur in low latitudes because of the high cold clouds, and temperatures drop off with latitude, and so does the humidity. Humidity is squeezed out with precipitation into higher altitudes, so very dry, stable air in the upper altitudes that we'll see makes a difference for some of the instabilities that we will discuss. Within that, you have features in the ITCZ, even though in the mean it looks like bands across the globe. Within it you have these kinds of features. This is for the Pacific, showing for July and August 1967 clearly eastward propagating features with some clusters that are also stationary, if you will. So these are called the easterly waves, which are also seen in the Atlantic and are associated with cyclones or formation of hurricanes that we will talk about later on. And Holton's ideas about how ITCZ is made up of these westward propagating features will also come up, which should remind you of the waves we generated by the diabatic heating. If you look at the variance in terms of OLR and for different seasons and different bands. So here it is for June, July, August, September, October, November, 2 to 10 days, 10 to 20 days, 20 to 60 days, 1 to 10 years. So you have low frequency stuff here, which is related to El Nino and other things. As we said before, the higher latitudes have much more of a multi-day variance that is much higher than in the tropics. I mean, the lower frequencies like 10 to 20 day and 20 to 60 day almost disappear at these latitudes, whereas the lower latitudes are rich in the 2 to 10 day band, as well as 10 to 20 days and 20 to 60 days, especially in the Indian monsoon region. So obviously that's the monsoon season, but if you go to September, October, November, the different regions light up. So you still have the end of the summer monsoon and the northeast monsoon happening here, and the seasonality of the low frequencies is also seen here, especially because El Nino, for example, peaks into September, October, November, and December, January, February. But as you go to December, January, February, you will clearly see a shift in the monsoon region, as well as the so-called great cloud bands that we talked about. Eastern Indian Ocean still remains complicated, especially even in the pre-monsoon season or the March, April, May season. So ITCZ is not monolithic even in terms of time scales. It has all these rich spectrum of time scales, from synoptic time scales or days to what are called intra-seasonal time scales, so especially the 20 to 60 day time scale. And the 10 to 20 day time scale tends to be referred to as the quasi-biweekly time scales, and then you have interannual to decadal time scales as well. So ITCZ is manifesting all those variances. We want to understand the relationships between mean sea level pressure, convection, that's what we're after, and sea surface temperature distributions. If you remember the mean sea level pressure and surface winds we saw before, we had the subtropical gyres, the trade winds, the the doldrums or the ITCZ here, and of course the seasonal change of the monsoon, southwesterlies, intermonsoons, northeasterlies, and the intermonsoons. The sea level pressure we look at here basically to look at the cross-equatorial pressure gradients. It turns out that the cross-equatorial pressure gradients are related to the low-frequency distribution of sea surface temperatures, and these cross-equatorial pressure gradients we will see play an important role in the instabilities that lead to convection and ITCZ, the bands, right? The other thing is to notice that the ITCZ is going to have regional features from east to west in the Pacific, which is so big. The Atlantic is going to be different, and the Indian Ocean, of course, is going to be very different. So CEPG is the cross-equatorial pressure gradient that we will talk about repeatedly in this chapter. To jump into the initial mechanisms that we will start to bring in, we will look at inertial instabilities, which in the tropics become what are called symmetric instabilities. So has to do with the perturbations and how the balance between pressure gradient and Coriolis in the horizontal and pressure gradient and gravity in the vertical are going to determine the restoring force, whether the perturbed parcel will come back or oscillate or go off in the same direction and so on. So we'll define those instabilities. This figure is basically showing sea surface temperature distribution with the scale shown here. So under the ITCZ there are warm SSTs, but to look carefully whether it really happens over the warmest SSTs or is there something else going on. And these are the contours, black contours, where the OLR, which is, if you remember, an indication of deep convection, is less than 240 watts per meter squared. If you remember, the deep clouds create cold temperatures at the top, so the OLR is reduced. It's sigma T to the fourth. So you look for minimum in OLR, which corresponds to deep convection. So this is for DJF, and you see the great cloud band here, and this has become much weaker. Whereas if you look at JJA, you have a strong deep convection happening here, and this gets squished into the maritime continent. But as we said before, you see that this seems to be anchored to the convection that's happening over here in the maritime continent. We'll come back to that again later. You also see the equator in white band, but this yellow line here is the zero absolute verticity line. If you remember, the absolute verticity is relative verticity plus planetary verticity zeta plus f, and the zero verticity line crosses the equator here in DJF and is completely north of the equator, corresponding to the ITCZ, and convection tends to happen to the north of the zero absolute verticity line, even though that's not always the case. Okay, so there are exceptions here and here, so this is more of an equatorial convection and not the ITCZ. This is the Pacific, and this is for the Atlantic and Indian Oceans. As we said, Indian Ocean is a bit bizarre. Atlantic is somewhat similar to the Pacific, with convection to the north of the zero absolute line, absolute verticity line in DJF and JJA, but obviously Indian Ocean has a very different behavior both in JJA and DJF. If you remember JJA, you get the monsoon and the marine ITCZ both happening. So we have to explain all these features. This caption basically describes the details that I mentioned. I'll come back to that in the next podcast, as this is already about 10 minutes. Okay.